of CH576, and in the last class we dealt with what is known as Liouville's theorem. Just small recap. In the last class we had this, okay, that the phase volume is conserved. That was the conclusion. Okay, and in other words, the total time derivative of this phase density, which is a function of position coordinate, momentum coordinate, and time, is 0. Total time derivative of phase space density is 0, because this is a consequence of your phase being conserved, the volume being conserved rather. Okay, and then he said, okay, what is equilibrium in this perspective? We said equilibrium is something where you take any ensemble average of a quantity, say any quantity, say O, which is a function of momentum and position coordinate. I take an ensemble average, it's an ensemble average. Okay, and this ensemble average is time independent. So it does not matter when I take the average now or after 5 minutes or after 5 nanoseconds, does not really matter. And you know, this ensemble average is defined as, you take this phase density, which should be function of t in general time, multiply it with this pq, and you integrate over all possible values of p and q, which is the volume. Since this time independent, this has to be time independent. And so an equilibrium density is a function of only position and momentum and position coordinate. Okay. And you also showed that this is possible when P equilibrium is a function of the Hamiltonian of the system. Hamiltonian of the system. Okay. So this is which basically means that you know that Hamiltonian is something like a constant of motion for a system, because Hamiltonian does not have any explicit time dependence. And in one of the classes we showed that the total time derivative of Hamiltonian respect to time is 0, and that is why it is called constant of motion. So the equilibrium distribution should be a function of your Hamiltonian. You can, other than also Hamiltonian, you can have a situation where you have other quantities which are constant of motion, like for example, you have a quantity like angular momentum. In that case, your equilibrium distribution can also be a function of Hamiltonian as well as angular momentum. Okay, and I've given you 2 examples. One example is called microcanonical ensemble, which we'll discuss in detail in the next class. For which it is actually for a closed, not closed, for an isolated system. And in this case, each member of the ensemble has same number of particles or molecules, volume, and energy. Energy is fixed. If energy is fixed, it is obvious that your energy has to be equal to the Hamiltonian of the system. So in other words, your distribution, equilibrium distribution, is going to be nothing but it is going to be proportional to a Dirac delta function. So this is a function when h equals to E, it has a value, a very large value, other is 0. So essentially this is the equilibrium distribution for a system which is in microcanonical ensemble. Okay, this we have discussed briefly in the last class. And the one more thing which you know very well is there is something called canonical ensemble, which will again I'll discuss later. I'm just mentioning here. In canonical ensemble, your equilibrium distribution is given by exponential of minus beta time h, where beta is 1 over kVt. And this distribution is very well known. Everybody knows. This is called Boltzmann distribution. I hope everybody knows this. Any question so far? I hope there is no question. Any question you can ask me in the chat or okay, so we'll proceed. Hope you can follow me. I'm sure you guys are there. I cannot hear you. Yeah.
Yes.
Yeah. Okay. So we'll start from here today. Just a recap, small recap, that the first postulate of statistical mechanics. Can anyone tell me what are the first postulate?
The time average is equal to the ensemble average.
Yes. I'm not writing in detail, but in shortly we can say that time average is equal to the ensemble average. And for ensemble average to calculate, you need a distribution function or density. So which I said is like rho, the function of P and Q. But this is for continuous. This is for system following classical mechanics. And you can have a system, but if the system is quantum mechanical in nature, for example, I deal with subatomic particles, or I am interested in quantum effects, quantum mechanical, then I have restriction on the moment and position because I have Heisenberg uncertainty principle, and rather I will describe the system in terms of eigenfunctions and eigenvalues, energy eigenvalues. And many times your systems are quantized. It has a discrete energy structure, And in that case, you will see that your ensemble average, which is not actually integral over P and Q, it is actually taken as a sum over all these microstates. And these microstates are actually like quantum mechanical energy states or eigenstates. Okay. So that is what I think I mentioned in the, I think I used a notation like this. And I said, okay, this is given by Pi xi, something like that, isn't it? Maybe I divided by 1 over n. I think I had divided by 1 over n, isn't it? Check your notes. The
Yes, sir.
notation I use. Yes. Yes. Yeah. So.
Sir, hello. Sir, I had a doubt here. Like, why do we have to divide by n when we are considering the probability?
Yeah. See, you don't here actually. You're right. You don't need to divide by n. Ideally, I should write p. I should write pi because probability itself is normalized to unity. Okay, but
Okay, sir.
it is depending on, it is actually, ideally one should write like this. Okay, like this. But if I assume that the probability is defined in such a way that your pi is not equal to 1, but I normalize to n, then I put n, something like that. But this is not very important, you will see later. Actually, once you have p, you don't need to write 1 over n, you're right. For example, if your p is Boltzmann distribution, which is exponential minus beta e, you have the normalization constant also, no? So the normalization constant will come here. So this n is more like the normalization constant shown here. Okay, it's more
Okay,
like
sir.
normalization of the probability. So yeah, there are some problem with notation because I'm switching between books. Sometimes you'll have problems. Anyways, but the idea should be, concept should be clear. Anyway, this is the first postulate of statistical mechanics. But then there is another postulate of statistical mechanics, and this is applicable only in case of microcanonical ensemble. Let me write down the statement, then I'll explain. So, the statement is systems of the ensemble. Ensemble means this microcanonical ensemble are distributed uniformly. That is with equal probability this equal probability is very important, over all possible microscopic states of the system. Okay. Okay, just a minute. So over all possible microscopic states of the system, in the language of of time trajectory each state is visited on equal number of times okay times if weighted enough. Okay, so I'll take a break for a second, for a few seconds, and come back. Yeah, so now let me explain this, what I have written. Okay, so yeah, so now it is clear what is microcanonical ensemble. It is actually a system which is completely isolated. It cannot exchange energy, cannot exchange particle, and the volume is fixed. So it is NVE. These are the variables which are fixed for this system. Can anyone tell me the following, because I don't see any get any sound?
Yes, sir. Yes, sir.
Yeah,
Yes, sir.
yeah. So this is how it is. Now this is a microcanonical ensemble. Now I'll explain this with example, of course. Now this postulate, this is called postulate of equal a priori. This is called postulate of equal a priori. So what does it mean? Or a priori postulate of equal a priori. So it essentially tells you that all the microstates are equally probable that correspond to the same energy. For example, I give you energy, say the system can have energy 10 joules. With this constraint, I can have different microstates, huge number of microstates. So this postulate tells you that I can have huge number of microstates that would give me this particular macrostate in this microcanonical ensemble, but the probability of having all these big number of microstates are equal. I cannot prefer a particular microstate. I cannot say this microstate is preferred or the other microstate is preferred. All are equally probable. Is this clear, the statement? The first part of the statement.
Yes, sir.
I have a macrostate NVE, but that can come from in a huge number of microstates. Okay, and for each microstate to occur, there is a probability pi. What I am saying that pi is equal. If sigma is the total number of microstate, then pi is 1 over sigma. Is this clear? So each microstate has equal probable. Each microstate is equally probable, has equal probability. if these microstates correspond to a macrostate that belong to a microcanonical ensemble. Okay, I fix the energy. I say it has a 10 joule energy. It has 10. It can have only 10 joule energy. With that constraint, I can have many microstates, and each of these microstates would be of equal probability. Why equal? Because we do not know whether one is preferred or other is not preferred. So we make this assumption. And this is a postulate. And this is called postulate of equal a priori, and it works fine, perfect. And Boltzmann was the one who first introduced this, but he had actually very hard time actually convincing people around. And end of the day, you know what happened? Eventually, he committed suicide, Boltzmann, because he was so frustrated because people were not believing him, not taking this postulate seriously. So this is one of the reasons why Boltzmann committed suicide. Anyways, this is the first part of the statement. I'll explain this with example. It also says that in the language of time trajectory, each state is visited on equal number of times if weighted enough. So if I weight sufficiently enough, my system under the position and the moment of the system keeps on changing. So my system undergoes through all the possible microstates. Okay, and all the microstates are visited equally, but we have to wait enough. You have to wait long enough. Is this clear? So
Sir,
if we
is
wait,
this for all kind of systems? It is always true, or there is
yeah,
some
this
condition?
is a postulate, so you don't question. Like quantum mechanics postulate, you don't question. So here also you don't don't question. The first statement is actually the equal a priori hypothesis. Equal postulate of equal a priori. The second sentence is actually an extension in the language of time trajectory. But what I'm saying that it is a postulate, so you don't question. You take it for granted. Okay. So because you have no prior information, you have no prior knowledge, there is no way of knowing which should be preferred, which should not be preferred. So the best thing we can do, we can say all are equally probable. So we don't put a bias, but only when my system is in a microcanonical ensemble, like dealing with a microcanonical ensemble. Okay, so I'll give you some example. Okay. So the example is, again, I go back to my famous spin system. Say, I say that energy has to be equal to minus mu times h. H is not Hamiltonian, it is the h is the magnetic field. And what is mu?
Magnetic moment here.
Yeah. And I have 3 spin system. And the magnetic field is in this direction, say whatever the direction is, say this direction. So I have situation like this. I can have how many ways I can get total energy minus mu h. I can have a situation that, okay, I'll use different color so that it looks nice. I can have a situation that, okay, one spin is up, first spin is up, second spin is up, and the third spin is down. What is the total energy for this arrangement? Not very difficult to calculate. No? Minus mu h plus minus mu h plus mu h. Yes, yeah. This is mu h, no? This is mu h. This is minus mu h minus mu h. This is mu h. Is the other direction. So the total is minus mu h. This is one way of having this total energy. What is another possibility? Another possibility is, can anyone tell me what is another possibility?
All up.
It would be up, down, up.
All up, possible, but total is mu h.
Up, down, up, and Down, up, up.
See, always you have to have 2 up, 1 down, and then you have to shuffle, isn't it? So I can have one situation like this, this. This is possible. Also, I can have a situation like
Yeah.
this. In all the cases, the total energy is minus mu h, isn't it?
Yes,
Yes,
sir.
sir.
But there are different microstates, isn't it? Okay, there are different
Yes, sir.
microstates. The microscopic arrangements are different. I'm describing this using some quantum number, for example, spin up, spin down, whatever, because it's not a classical mechanical system. So what is the message here? The message here is that I cannot say this is more probable or this is more probable or this is more probable. What should I say if I follow equal a priori
Equally
postulate?
probable.
I should say that all these microstates are equally probable. Is this clear?
Yes, sir.
Okay, all are equally probable. So this is an illustration of what is known as postulate of equal a priori. So, okay, from the very beginning, we say that all these microstates are equally probable. Of course, if I now change this constraint to 2e, something else. So, for example, I change this constraint to 3e, or plus mu h, for example. Then there will be another set of microstates, isn't it? So those microstates will be equally probable, corresponding to a macrostate which has energy E equals to plus mu h. But that will have different microcanonical ensemble. Is this clear?
Yes, sir.
Yeah,
Yes,
it is
sir.
not very difficult. It is very easy. It is not very difficult. Now I have this. This is postulate 2, postulate 1, postulate 2, and then we have something known as ergodic hypothesis. A consequence of this ergodic hypothesis is that time average is equal to ensemble average. But what is this ergodic hypothesis? So the statement is as follows. I'll just write down the statement. During its trajectory in phase space, a system is free to explore all the microscopic states. And given a sufficiently long period of time, the time spends time in a state that is proportional to the volume of the phase space. volume of the state in phase space. Now just check whether this statement is clear to you, because this is a very important hypothesis. A consequence of that is time average is equal to ensemble average. So basically a system is any system. I have n number of particles in a box, gas molecules, they are moving around. So the position and momenta, they are changing with time. So it has to go through all the possible position and momenta within that box available, possible. But you have to wait sufficiently long. Okay. And if you wait sufficiently long, it will go through all the possible microstates. Is this clear? And the times it spends in a particular state, microstate, is proportional to the volume of that state in the phase space. So how much? So tinier the volume, so less. So essentially, you have a smaller box, then it will explore the number of microstates much earlier. If you have a bigger box, you have to wait long enough. Is this clear? This looks obvious, but this is a hypothesis, of course, because we assume that that if you wait sufficiently long, then my system will go through all possible microstates. Is this clear, the statement?
I'm not able to follow the statement that time spent in a state is proportional to the volume of the state in the phase space.
No, it basically tells you that, see, you have to wait long enough in order to explore all the possible microstates. So if the phase space volume is tiny, tiny means what? You have some restricted momenta and position coordinate. Then the time spent will be less. So as your phase space volume increases, your time spent is also going to increase, isn't it? See, if you have a bigger phase space, then it will take the system much longer to explore the phase space. If you have a smaller phase space, then the system will explore that smaller phase space much earlier. That is what I am saying here, nothing else.
So that volume of the phase space, is that a characteristic? That is a characteristic of the macro state. Is that what you're saying?
No, this is the volume of the state in phase space. Volume of the state in phase space. So the microstate is not the full phase space, no. It's a tiny volume, that dpdq kind of thing. That is your microstate. Okay, because that is a very small value of p and q. And that volume is proportional to the time in the phase space, it says. Actually, if you go to quantum mechanics, you will see that this volume of the phase space has unit of action, because it is position times momentum, isn't it? So which is a function, which is action, which is like joule second, arc second, this kind of thing. Also, it has the same unit as Planck's constant, and the smallest possible this phase space volume is Planck's constant h. Okay. So h
is that where least action concept comes from?
No, least action concept does not come from here. That comes from your classical mechanics. The least action is something like that. If you define something like action, which I did not do, you take the Lagrangian and integrate the Lagrangian, say from some time initial to time final, and what you get is your action, and along a path, your action is minimized. Not minimized, it is actually the first derivative of that action along that path is 0. And that leads to what is known as Newton's equation of motion. So along a trajectory, your action is minimum. This is called principle of least action. Okay. But what I am saying here, that the phase space volume, the tiniest phase space volume possible is your not Dirac h, Planck's constant h. It is proportional to the Planck's constant h. Okay. So in other words, if I write dp times dq, the smallest possible dp times dq is h. And if you are doing in 16-dimensional space, this is obvious that d3np d3nq, it is proportional to the h to the power of 3n. This is the phase volume. Okay.
Okay, sir.
tiniest or the smallest volume element. Why you cannot go below this? That is because of quantum mechanics. Because quantum mechanics tells you there is something called Heisenberg uncertainty principle, which basically tells you that whatever experiment you do, whatever instrument you have, you cannot violate this. You cannot simultaneously measure momentum and position and the corresponding position of a system, of a particle rather, with infinite precision. The best thing you can do, that the uncertainty in momentum and uncertainty in position, if you multiply these two, it is proportional to Planck's constant. Kailash, you know this, no? That is why
Yes, sir.
the tiniest possible phase volume is in the order of Planck's constant. And you will see later that if you take this exactly as equal to the Planck's constant, then if you do the calculation, then all these things, all the things you calculate, they actually match with your experimental value, and also with and you experimental value, and also you can get the free energy profile, everything which you get in thermodynamics. You also connect to thermodynamics, but you have to take this tiniest, the smallest phase volume as equal to Planck's constant in in like if you have one position coordinate and one momentum coordinate. If you have 3n position coordinate and 3n momentum coordinate, then it is h to the power of 3n. Okay, so h is Planck's constant. Okay, any question so far? Because this subject you have to go a little slow initially. It is not that how much I cover, it is how much you understand, how much you learn. That is important. Okay, now the next question comes, and coming back to Kailash, do you think that all the time this hypothesis will be valid? I'm asking this question to all the students. Anyone can answer. Do you think that this postulate is all the time valid, or you think that there could be a violation, a breakdown? Anyone can answer. At
One
least try
thing
to
that
answer.
appears out of these hypotheses is that we
Who
are
is this?
consistently
Who is
talking
this?
about
Who
the
is this?
Vatsal. Vatsal.
Yeah. Tell me.
Throughout these hypotheses, we are consistently talking about the time scale of our observation. So we probably cannot observe at too short time scales, such that
Even if you observe, so I'll give you an example. So what is there? This is a bottle, no? Bottle of water. So you have water molecules inside, no? So do you think that if I take this water molecule at this room temperature and pressure, and that this water molecule, this system of say 1 liter, whatever, water, that is ergodic? What is your guess? If I calculate, for example, some thermodynamic quantity of this now and after some time, will that be same if I keep the temperature constant?
it should be, right?
It should be, yes, you're right. So in this case, that system is ergodic, isn't it? Now,
Yes, sir.
yeah, but not all the systems are ergodic. So can anyone guess that maybe in this room you have something, a material which is not ergodic? I'm sure also in your room you have a material which is not ergodic, which you use almost every day. I think every day, yes. If not every day, or almost every day. Any idea, any guess? Kailash, any guess?
No, sir.
Yeah, the answer is glass. This one. The bottle is made of glass, mostly silica, whatever. So glass is a material which is non-ergodic. How many of you knew this? And glass, molecular glass, is actually a very, very active area of research in physical chemistry, chemical physics, and condensed matter physics. People are still trying to understand glass. What is glass? Can anyone tell me?
Amorphous form of SiO2.
No, SiO2 is one example. I can have different types of glass. SiO2 is just a common example. I can have metallic glass. I can have many other materials that are forming glass. Even people say that even molecular cell, some parts of molecular cell, they also behave like glass. What do you mean by glass?
So it is a metastable state.
Yes, you're right. Actually, glass is neither a solid nor a liquid. It's more like a solid, amorphous solid, you can say. But it also has liquid property. It is still flowing. You cannot see because it's flowing so slow. So it is in a metastable state. It is not in equilibrium. Ergodic hypothesis says that if you OS sufficiently long, that your system will go through all possible microstates. It is still trying to go through, but it is trapped. So the material is made of these molecules or particles, whatever. You have a underlying landscape, energy landscape for this material, and the particle motion is already trapped in this landscape, and they're trapped in such a way that it cannot explore all the possible microstates. You have to wait sufficiently long, and this time scale is longer than the time scale, the age of the universe, in order to behave in order to have a glass which is ergodic. This is a trapped state. This is a metastable state. So if I draw an energy landscape for a glass, very qualitatively, if I draw, it will be
So is
something
it
like,
characterized by barriers?
yes. So it is like there, like there, like there, like there, like there, like there. This is an energy landscape of a glass. Of glass. Now what happens? You can think that your system is trapped here. If it is trapped here, then if you wait for some time, it will escape. No, the barrier is small. Okay, so it will come here. But if it goes there and gets trapped here, this barrier is very, very large. Huge barrier, isn't it? This is very qualitative, what I'm saying. So the system will get trapped there. It cannot really escape, and it cannot go to this state, this state, this state. And in order to go there, it will get trapped here again. It goes here, it will get trapped here again. So like this. So your energy landscape is bumpy and rugged. It's called rugged energy landscape. Okay, so energy landscape is rugged. Okay, any question? Any other example? This is very interesting, and this is a top class people are working in this area, and where you can use statistical mechanics, equilibrium and non-equilibrium statistical mechanics. Even actually, if I take, for example, you know this cell membrane, you know, the lipid membrane in cell.
Yes, sir.
Made of protein and lipid. People have shown using computer simulations that they are also behaving like glass. They have this glassy kind of behavior. So in many biological contexts, you have things which are behaving like glass. Even proteins, the proteins, they also behave like glass. So if you there are examples where proteins behave like glass. There is something called dynamical heterogeneity, which basically means your energy landscape is one snapshot. It's changing as a function of time as well as function of space. So in some space, the dynamics is fast, some space is dynamics slow. And the space which is faster now, it will become slower later. And the space which was slower will become faster. So there's a temporal as well as spatial heterogeneity. This is another signature. or characteristics of glass. Okay. And then another example is there, which is very close to glass. This is called supercooled water or supercooled liquid. Under high pressure, you can keep the water, even liquid, at a very low temperature. This is called supercooled liquid.
That is also metastable state.
That is also metastable state. And if you calculate thermodynamic quantities for such systems, time average will not be equal to ensemble average. So there you'll see a breakdown of what is known as ergodic hypothesis.
Hello, sir.
Yes.
Sir, essentially these systems are non-equilibrium systems.
These are actually non-equilibrium system. And ergodic hypothesis means that you have spanned all the microstates. So essentially you are being equilibrated. So any system which are trapped, metastable, non-equilibrium, your ergodic hypothesis will break. Even in our lab, we do simulations of, say, small molecules diffusing in a very crowded environment. And the molecule can go and get trapped in one of the pockets, come out. Okay, it is seeing obstructions. So in all the cases, and if you have a sticky zone, like a region where it is sticky, the molecule goes there and gets stuck there. So you will see that in those cases, time averages and ensemble averages are not equal. So they are not in truly equilibrium, but we do a double averaging. These are technical things. Or we do ensemble average and you assume, okay, this ensemble average is good enough so that it matches with some experiments. Now, experiments are also done within a finite time scale. No? So then it matches with experiment. But there are cases where they don't match. And I'm not going in detail, but there are cases where you see that this ergodic hypothesis is not valid. And you can actually measure how much your system deviates from ergodicity. There are actually prescription to calculate the deviation from ergodicity. If you're interested, you can go and read papers. I can tell you. Okay. Any questions so far? So this is non-ergodic. Another thing would be super cold liquid. This is a very, very active area of research in physical chemistry. So you have to understand physical chemistry is not only about doing quantum chemical calculation of some molecules and looking at their dynamics. You also look at collective phenomena and connect your calculation to thermodynamic quantities. And these are fantastic systems where you have this ergodic hypothesis being broken and many other interesting phenomena going on. Okay. So I have a question now. Let me ask you another question. So far, I have introduced the postulates. I've told you that time average equal to ensemble average. What is the utility of the first postulate? The time average is equal to ensemble average. Tell me. What is the utility, or why would I be interested in this postulate? Why it is useful rather? Can anyone tell me?
So because we can do experiments or we can perform simulations for a particular time interval for a particular time. It is like time average. We cannot use time as infinite, a very long time.
Very good.
So in that sense, we can take the ensemble averages.
Very good. Very good. You got it. Who is this?
Nashit.
Yeah, Nashit. So you got it. So others got it or not? So the idea is as follows. The time average, strictly speaking, it should be average over a very long time. So I have to follow the trajectory of a huge system, Avogadro number of particles or even more for long enough time in order to have a meaningful time average, isn't it? That is not possible all the time. So what you do, rather than doing that, you run short trajectories, but many trajectories, and each trajectory is like one ensemble. And you average over many trajectories. It is like averaging over ensemble, because when you average over many trajectories, you are constructing a histogram or a distribution, ensemble distribution. Okay, so indirectly you do ensemble averaging and you infer that it is equal to time average and that is equal to eventually equal to thermodynamic quantities. Okay, is this clear? I'm making it very simple.
sir.
I'm not
Yes, sir.
complicated. So in reality, I cannot follow 10 to the power of 30 particles over 1 hour, for example. The amount of position and moment I have to store, I cannot store in any computer. Okay, you can, but rather you can compute say 10,000 particles, say for 1 microsecond, and then you do the simulation for several ensemble, and then you take average over ensemble. In reality, you take a double averaging. Actually, you do ensemble plus time averaging, and then you will say, okay, this averaging is sufficiently good now, and this will try to match with experiment, and it matches. And this is the strength of statistical mechanics. Okay, we don't solve the equation for Avogadro number of particles. You solve equation for small number of particles, but we throw many trajectories, and that too is also finite. And I do averaging, and after averaging, we calculate. We see this is good enough to actually compare with experimental results. The strength of statistical mechanics, and the modern theoretical chemistry is mostly statistical mechanics, and people are using machine learning and other things in recent days, because quantum mechanics you cannot perform for big molecules. You have to do some approximate method, you have to calculate on a computer. Of course, everything is fine, but you cannot do very accurate calculation. So rather than asking these questions, people ask more questions like, what happens to this pressure, volume, what happens to phase transition, at what temperature this phase transition will occur, like this kind of question. Okay, what is the, for example, the magnetic susceptibility of this material? All these things you can calculate using statistical mechanics. It's a very powerful tool. It is used in physical chemistry, in physics, it has applications in biology. It is everywhere. It's a beautiful subject. So far I have introduced a little bit of classical mechanics, Legend transformation, okay, postulates, okay, Liouville's theorem, all these things. And today, now, rest of today, we'll discuss a little bit of statistics, probability and statistics. It has nothing to do with the statistical mechanics, what I'm doing. It has connection, of course, but it's like a detouring. Okay, we'll detour and we'll just for an hour or so, we'll discuss, not an hour, I don't have an hour, but for some time, we'll discuss this probability and statistics. So how many of you had actually a course in probability and statistics? How many of you had? Just tell me.
I think we did data analysis last semester.
Who is this?
Anish here.
Anish, okay. Okay, data analysis.
Yes.
Very good. Okay. So it was taught by whom?
Professor Anil Kumar.
Okay. So actually you have some exposure. Very good. So we'll do our way, my way of doing things. Actually, it is slightly different, but we'll do that. So for example, if you're a chemistry student, you go and do titration, no? I do 10 titration, I get 10 values. And I do 100 times, I'll get 100 values. You'll see that some of the values you're getting, say, 4 times, some of the values you're getting 5 times, some of the values you're getting 1 time, like this, isn't it? This is a everyday experience kind of thing. If you do so many titration, for example, or if you measure anything. So in a result, any measurement, it gives you a value, but the probability of having that value is also finite, isn't it? It comes with a probability. And not all the values are equally probable. Here, you understand what I'm saying?
Yes, sir.
Isn't it? If you are good enough, then you'll get a value which is close to the value you should get. But if you are not a good lab person, you'll get scattered value, and you have a very wide distribution of your distribution. We'll talk about it later. But let us start like this. Say we are doing an experiment which has n possible outcomes each with probability Pj. So it is obvious that J goes from one to, because up to small n. So say I do it for 10,000 times, for example. Okay, it's not a very difficult. N possible outcomes, each with probability Pj. And if you do this, perform this experiment many times, okay, then you would expect is we expect that this Pj, this probability Pj, okay, let me write down this. This is something like limit capital N goes to infinity, Nj divided by N. J I have told you it is 1 to up to small n, and Nj is the number of times of outcome J, and capital N is the total number of repetitions of the experiment. Is this clear? What I've written here? Not a very difficult thing to do. I do it 10,000 times, 100 times I get one value, 70 times I get another value, like this. I get same. Okay. So then it tells you something, of course, that if I sum over Nj, what should I get? Sum over Nj,
N.
I should get the capital N, isn't it? In my notation, huh? Of course, and if I sum over Pj, what should I get?
Unity.
I should get 1. Is this clear? And of course, Nj is less than N, so Nj by N is less than 1. So Pj is less than 1. But what are the two extreme values of Pj? Pj is 0 or Pj 1. Pj 1 means you are very good. Every time you do the experiment, you get the same value. Okay? Then your Pj is 1. And if you are extremely bad, then Pj is 0, isn't it? Okay? Is this clear?
Yes, sir.
So Pj is 0 means it is impossible, rather. Okay. So this is how it is. This is a discrete probability. Okay. This is a discrete probability, of course. It's a discrete. Because now, if it is discrete, then average x I can define is like this. I'm sure you guys know this, average x. And I'm using this notation x within angular bracket. What will be the expression? Can anyone tell me?
Sum over J, X, J, Pj.
Yes. Is this clear? Any query? Any question? Ask me. Okay, so I can draw this actually. For example, I draw this like this. Say this is your p-axis, which is a function of x in a way, but x is like discrete. You have these values of x like this. Some of the x occur with higher probability like this. Some of them occur with lower probability. Some of them with medium probability like this. Okay. So height tells you the value of Pj, isn't it? This is like x1, x2, and this is maybe x47, this is x48, like this. You understand? This is how it
Yes,
should
sir.
look like. No, this is very simple. This is called average x, also called the fast movement. You know this language of this distribution, this probability distribution. Okay. How many of you knew this term, first movement? How many of you? Tell me at least.
I think I've heard of it. The second moment is,
So
I
now
think,
if I have first moment, I should have a second moment, and second moment is this average of x square.
variance. Oh,
This is the second moment. This is what will be the answer? I hope people knew about it, or you did not know the name, second moment. Kailash?
I had heard about these things. First moment, second.
Okay. So another thing you can define is called the second central moment or variance. What is the definition? This is given by this sigma x square. This is the notation usually. You remember this? Let me tell you how to do this. Take any value of x, subtract its average value from it, then make a square of the whole thing and take an average of this. This is called the second central moment or variance. How many of you knew this? This is done, I'm sure, in
yes,
your
sir.
Yes,
course.
sir. Yes, sir.
I don't know how it is done, but this is how it should be done. So I can write this also using my this sum notation j into 1, 1 to n rather, xj minus x average whole square into pj. This is how it should be, isn't it? Actually, it
Yes,
is
sir.
a measure of spread of the distribution, isn't it? You'll see. It is not very difficult to understand because see what it tells you. Your distribution has a mean. X minus x mean how much deviate from the mean. You take a square of it, which is a positive quantity, and take an average. So on an average, on both sides of mean, how your values are deviating, isn't it? So it is a
Yes, sir.
spread of the thing on both sides of the average. That's the spread. And by definition, looking at it, by definition, it is positive real quantity. Positive. It could be 0, of course, by definition. By definition, it is this. Okay? Greater than or equal to 0. Is this clear that is greater than or equal to 0?
Yes, sir.
Yeah.
It
So
is
because
0 if and only if xj equal to x mean for all
yeah,
j.
Yeah. Sometimes I have this problem. Anyway. Okay. So now let me expand this. If I expand sigma x square, what I'm going to get? I'm going to get this is xj square minus 2xj x average plus x average whole square whole thing multiplied with Pj. This is how it is.
Yes, sir.
And if I expand this, the first thing is what? Xj square Pj sum over j. I'm not writing. Okay, I can write. Next one is 2 Xj Pj into X average. And then X square sum over Pj. What is this? Xj Pj X average?
X average square.
This is X
X
average.
average.
So and multiplied with another X average. So this will give you X average square. What about this? This is X square average, isn't it?
Yes,
And
sir.
what
Yes,
about
sir.
this? This is unity. So what I have end of the day? X square average minus 2x average square plus X average square. So what is this? Answer is X square average minus X
X
average square.
average.
Now I know this is greater than equal to 0. What does it mean? It means that X square average is greater than equal to X average square. Okay,
Yes, sir.
this is done. No, I think in your the course you took, this was done.
Yes, yes.
Yeah, so you can follow. No,
Yes, sir.
for some reason this eraser doesn't work anyway. But what about the continuous distribution? So far we talked about discrete distribution. So let us talk about continuous distribution. So continuous distribution is something like that. The probability of having a value between x and x plus dx is given by something like p of x times dx. You understand this statement, no? If the distribution is continuous, then what is the probability of having a value x and a small deviation from x plus dx is given by the probability distribution itself, px times that small difference dx. Is this clear?
Yes, sir.
It's not a very difficult thing, of course. And of course, this probability distribution has to be defined within a limit. So I say it is defined in the limit minus infinity to plus infinity. This is my definition. Say I can have a different situation, of course, I'll tell you. So if that is so, then if I take this integral px dx, what is the answer?
Unity.
Unity.
Because it is normalized, isn't it? Our total probability is 1. Isn't it? What about this? What is this then? This is your x average.
X average.
What about this?
X square average.
This is x square average. And what about this? This is your nth moment, isn't it?
Yes, sir.
Okay, so let us take an example. So I give an example that, okay, px equal to a constant a. When you have a px in the interval small x is between small a and small b, it is 0 otherwise. So can you draw this? We should be able to draw this, isn't it? Your Px. So this is your A, this is your B. So between A and B, it has a constant value A, capital A. So maybe this is the value, no? It's like a box, isn't it? Because less than A or greater than B, it is 0. So it's like a box function. Is this clear, the way it is defined?
Yes, sir.
How do you, what is the height? How do you calculate the height of the box function?
That is defined to be A, but we can get it from the normalization.
Yeah. So what you should do, you should normalize it. So let us normalize it. So Px dx, of course I have to integrate between A and B because it is only defined within A and between A and B. And if I do this, you have capital A coming out. So you have dx A and B. And that has to be equal to 1, which basically tells you A into B minus A equal to 1, or A is 1 over B minus A. So what is the height then? This height is nothing but. Fine? Is this fine?
Yes, sir.
Okay. What about the fast moment? X average. You have to calculate. It is 1 over B minus A to B, X dx, isn't it? This is 1 over B minus A, X square, sorry. Sorry, x square by 2 ab. What is the answer? It is b square minus a square
By 2 B minus.
Yeah, but you can further simplify. This is half b plus a, isn't it?
Yes, sir.
What about the second moment? I'm just giving you some example, that's all. What of the second moment? You can calculate the same way, no?
B cube minus A cube by 3B minus A.
Yeah. You can calculate the same way, the second moment. Not very difficult to do. So if you calculate the second moment, it will be 1 by b minus a x squared dx kind of thing between a to b. That is how, no? Yes. And this is equal to 1 by b minus a 1/3 b cube minus a cube, isn't it? And you know what is b cube minus a cube? It is b minus a b square plus ab plus a square, isn't it? This should be like this, isn't it? I hope I'm not doing anything wrong. 1/3 b square plus ab plus a square. You check yourself whether it is matching. Is it matching? Did you do yourself?
Yes. Yes, sir.
You should match.
Yes, sir.
And then what is the variance then? Remember the variance, definition of variance is x square average, easy to remember, minus x average square. So x square average is, you know this, 1/3. What is x average square? You remember what is x average? It should be 1/4
B plus A by 2. B square plus A square plus 2AB.
And if you further simplify this, I can write down the answer. If you further simplify this, you get something like b minus a whole square by 12. One line, I don't want to do it. Okay. And
Yes,
you
sir.
can also calculate the root of this variance. This is called standard deviation. You know this. Maybe this is, and what will be the standard deviation in this case? It will be 1 over root over 12 into b minus a. Isn't it?
Yes, sir.
Okay. Now give me another example, which is the most common continuous probability distribution. What is that, you know?
Gaussian.
Yeah. I think everybody knows in this course. And this is called a Gaussian or a normal distribution, isn't it? So I define this as Px as C, some C times e to the power minus x square. So let us call it 2a square. This is a Gaussian distribution, and this is defined in the limit, in the range rather, minus infinity to plus infinity. Everybody knows about this distribution, this Gaussian distribution or the normal distribution.
Yes, sir.
If you
So
plot it, you know how does it look like, no? Of course, because if we make x to minus x, it does not change. So it is symmetric, it's a symmetric function or even function, and it will be like this. In the long x plus minus x limit, you go to 0, other it's a bell-shaped curve, isn't it? You see, this is your Px equal to this. You know this, no?
Yes, sir.
Just a minute, give me a minute. So let us normalize this function. This has to be equal to 1, which basically means your C is coming out. Now I'll give you a standard integral. You can derive the standard integral, but I am giving you. You can derive the formula if you want. This is e to the power of minus alpha x square dx. You know the answer? This is
Root
root
by
pi
alpha.
by alpha.
this is the answer. Okay, root over pi by alpha. Okay, the standard integral. So if you take a Gaussian function, you integrate from minus infinity to plus infinity, this is what you get. So if you do here, your alpha is equivalent to here 1 by 2a square, isn't it? So what will the answer? Your answer will be 1 equals to constant is there, c. Your pi is there, root over pi, and you have to have 1 over root over alpha. So you should have 1 over 1 by 2a square. What is this? This is c root over pi root over 2 into a, isn't it?
Yes, sir.
Okay. So this also gives you, allows you to express c in terms of a. What is then c in terms of a? It is 1 over root over twice pi a square.
Square.
Huh? Can I write like this?
Yes,
Yes,
sir.
sir.
So your distribution function becomes what? Function becomes, actually because of the normalization, you see I have only how many parameters that describe the distribution? I don't have 2, a and c, I have only a. If you give me small value of a, I also know the normalization constant. isn't it? Is it clear?
Yes.
So if I take at x is equal to 0, what will be the value?
1 over a root 2 pi.
So basically, the peak value, which is at, sorry, sometimes I have, yes. Yeah. So the peak value is this. No, 1 over root over twice pi s square. And then you have this. And this width will be defined by this A. We'll see in a few minutes. Okay. Any questions so far? What is x average? With respect
0.
to this distribution. How do you know this is 0?
The integrand is odd, so minus infinity to positive
Yeah,
infinity.
because the integration is of an even function times an odd function, which is x, within a symmetric interval. So the integration is 0. So what about xq average?
That will
Or
be
x power
non-zero.
n where n is odd.
Yeah. So your xq average is also going to be 0. So I can say actually x to the power of n average is 0 if n is odd. Okay.
Yes, sir.
This is the reason, isn't it? So all the odd moments of a Gaussian distribution is 0. Is this clear? The statement?
Yes,
Yes,
sir.
sir.
So all the odd moments of this Gaussian distribution is 0. What about the even moments? So what is the simplest possible even moment you can calculate?
X square average.
Okay, so let us calculate x square average. We don't have much time, but maybe we'll start and then we'll continue in the next class. So the x square average you have to calculate. Into 1 by root over twice pi square. This is the integral. How can you calculate this? So this constant you can take out, no? This constant you can take out.
Yes, sir.
And any suggestion how to calculate this integral?
So using the standard integral.
Standard integral. Then actually I'll tell you how to do it. Say let us call I have this integral, no, I. What is the answer?
Root pi by
Pi
alpha.
by alpha.
Okay. So now what I do, I just take a derivative of this integral with respect to alpha. What I should get? What is the answer? Your answer is going to be minus x
minus
square.
x e power minus alpha x square dx.
So it basically tells you that your x square e to the power of minus alpha x square minus infinity to plus infinity is given by minus di d alpha. Is this clear? I just multiplied both sides with minus 1. Huh?
Yes, sir.
And this is equal to what? Minus of
Root
n,
pi by alpha
pi is there, n x to the power of n minus 1.
minus 3 by 2.
Isn't it? N x to the power of n x to the power of minus 1. But this minus and minus will cancel, isn't it? This fine?
Yes, sir.
So what is the answer? It is actually 1 by 2 alpha. I think it is like that. If I rearrange it, it should be like this. Just check and tell me if it is correct.
Yes, sir.
Okay, so now we know the answer, that alpha is equivalent to 1 by 2a square, no, in our case. So your x square average is going to be, this constant is there, 1 over root over twice by a square is there. So this integral will give me what? X square this. This will give me 1 over 2 into 1 by 2a square into pi by 1 over 2a square whole to the power of half. So let us simplify this. So this will give you a square. This will give you root over twice pi a square, isn't it? What is the answer then?
A square.
A square. A square. So this is your a square. So what about then sigma x square in this case, which is your, what is the definition? X square average, x
minus
square
x
average,
square.
x average whole square, isn't it?
Yes, sir.
This is the definition, no? Just check. That is the definition, no?
Yes, sir.
And this is equal to what then?
A square minus 0.
A square. So this also tells you what? You can actually write your distribution as twice pi sigma square variance. Is this clear?
Yes, sir.
Yes, sir.
So we'll start from here in the next class. We'll stop here today. Okay? So I am now stop recording.